on Sub-Riemannian geometry, and we'll focus mostly on the curvature, the Tanaka-Webster connection. So my goal is to define curvature on this Pseudo-Hermitian type of structure, which is kind of analogous to the Riemannian case, but with some twist. There's something different here. And essentially, our goal is to prove an identity that connects the Sub-Riemannian or the Tanaka-Webster curvature with the Levi-Civita curvature, the curvature of the Levi-Civita connection. So we have essentially three parts. First, I will introduce you to this method of moving frames in Riemannian manifolds. So we can see this method, which is it's a very useful method to study curvature. Essentially, what this does is it helps us compute the curvature in a very easy way, in contrast to the Koszul formula, which is more messy, I'd say. And then we'll define the curvature. We'll see this identity that I mentioned, and at the end, I'll give an example. So let's begin. Okay, now the method of moving frames. So what is this? So think you're on a manifold and you carry essentially kind of a coordinate system on you. So as you move along the manifold, this changes in a very specific way. And this essentially is captured by what we call a connection form. So what happens exactly? We want a way to essentially capture this coordinate system and how it moves, in the around the manifold. So how do we do this? We essentially take an orthonormal frame on a Riemannian manifold, and we take its coframe, which is this omega1, omega2, omega n, and that's the frame. Frame is x1 to xn. So once we have this dual frame, we define the connection one forms by essentially this expression here, which is the Riemannian product of this Levi-Civita connection of those fields, and this is essentially the definition. Now we can solve this also for this, because this is orthonormal. We can also write it like this. And using this connection form, we have the first structure equation, which is this thing. Now, what is this? This is torsion, and this is a two form here, and this is written like so. So it's the derivative, the exterior derivative of omega I plus this sum here, which is theta ij. You see here is just the connection form, and omega j are just this dual frame here. Now we are in Riemannian geometry, and we know that the torsion vanishes with the Levi-Civita connection. So this thing is zero. So the equation kind of simplifies here. So this thing, okay. Now, because we have this compatibility of the connection with the metric, the connection form satisfies this property here. This essentially they are skew symmetric, and this essentially helps us uniquely determine those connections. Otherwise, we will not be able to find them. So we need this compatibility. And we will see in this example how this works. Okay, moving on. Now, the second structure equation is essentially the curvature equation. So the curvature is just this phi ij, and it's written like this. So I'm using, so this is the exterior derivative of the connection forms, and this is the wedge product. Again, this is the second equation, and we can find the curvature. We can write it in this frame like this. Now, the curvature forms are also skew symmetric. So essentially, where this helps us essentially compute the curvature. This is a very easy way because we use exterior derivatives instead of the connection, what's it called, the covariant derivative. So in general, this is easier to work with. Okay. Okay, here, essentially, here we just can also do this for submanifolds. So if you consider submanifold, you can essentially find the second fundamental form using this formula here. So you can also use this for submanifolds. Now, let's give us some setting of where we're about to talk. Now we consider a local frame. Now we switch to the Sub-Riemannian setting. So we are in the Pseudo-Hermitian structure, and we just fix a local frame T1 to Tn, and this is a frame of this T10, as we talked in the previous time. It's defined on an open cover, open set U. This is just part of the cover. And we have this kind of notation, T alpha, T or A maybe. It's just this T, which is T is the Rib vector field. T alpha here is just essentially this frame. And T alpha bar is defined like this. So T alpha bar is just the complex conjugate of T alpha. So and alpha runs between 1 to n. So we also said that T0 is just the Rib vector field T. Okay, now we can define a coframe. And the coframe is just theta alpha, and theta alpha bar, which is alpha bar is defined in a similar way as this thing. We also define this alpha x and y to be this g theta, which is g theta is just the Webster metric that we talked in the previous time. And we have the torsion, because here we have, as we said, the Tanaka-Webster connection has torsion, and this is the torsion 1 form. So I mentioned previously that the torsion was a 2 form. Essentially, this is a 1 form here, but we wedge it with another form, so this becomes a 2 form, but this is 1 form. And we have x and y. So for all x and y in Tm. Okay. And we have this final definition that we find h of a bar vita equals to L theta, which L theta is just the Levy form, as we mentioned in the previous time. I will remind you exactly what this is in a minute. And we have T alpha, T bar vita. Now, let me remind you of this theorem we proved the previous time. So this is a unique connection. We call it a Tanaka-Webster connection, and satisfies all this. So it's compatible with the Levy form of the Webster metric, essentially. Then preserves the CR structure. And we have a torsion, of course, which is non-zero. And if it's zero, then we have another type of manifold. We call it Sasakian. So the Levy form, essentially, this thing here. So this is the torsion, and this is the Levy form. We also define the TUF equal to this torsion equal applied on T and X. So it's this thing. Okay, now let us define the curvature term tensor for the Tanaka-Webster connection. Now we see that definition is very similar in Riemannian geometry. So we just use this kind of relation that we have in Riemannian geometry, and we take those sections of this tangent bundle of M. Now we see some properties of this curvature. So the Webster metric of this thing x, y, z, w equals to minus the Webster metric, of r, y, x, z, w, and minus g theta r, x, y, w, z. So those properties are similar to the Riemannian ones. However, this property, this symmetric property, we have essentially x, y, z, w, that is equal to zw, x, y. This is not longer true in our case. So this gives us essentially the difference, one of the differences that the curvatures have in Sub-Riemannian geometry, and specifically in the Pseudo-Hermitian type of geometry. Because here we want to use the Tanaka-Webster connection. In a more general Sub-Riemannian manifold, we don't have a Tanaka-Webster connection because we don't have a CR structure necessarily. A Sub-Riemannian manifold is more general than that. And in this setting, we have other connections that are canonical. I think there is a paper by Latke that has this canonical connection for contact Sub-Riemannian manifolds. And there is, I think, another paper that I can't recall right now that gives a more general type of canonical connection that I think does not require not even a contact structure. So can go even more general than this, but here we just want this structure. Okay, now we'll define sectional curvature, and that's very similar to the Riemannian case. So you see here, we can use this notation in a similar way as for the Riemannian geometry. So we set R of ZWXY, that's defined as the Webster metric of this thing, Webster product, let's call it, R, X, Y, Z, W. So this is very similar to the Riemannian case. And we can write this index notation. You can use, if we want to talk locally. So we use this index notation here. And we have a definition of the sectional curvature. So we do it locally first. So we take a point on a manifold, essentially this Sub-Riemannian manifold, and we just define as G1H all the planes that are in this tangent space here on the point X. And then essentially of all those points, of all those planes that we have, this essentially this we can take the union for this, and this gives a fiber bundle, and we can define a function k theta, which is from this bundle to R, defined like this. So remember, rho is just this thing here, and this is a linear basis. This is not a frame because we're locally right now, but it's a linear basis satisfying this thing. So yeah, at a point X, but we can also extend this to the entire manifold. So essentially this is sectional curvature. Now let's move to the structure equations. So remember, we just talked about the Riemannian case. Now here, they're very similar, but we have this twist, this torsion, which is an extra term here. So let's see exactly how this look like. First of all, we have this. This is the contact form, and we have a derivative of this contact form. It's just this thing, 2i of HA beta of this thing, of this wedge product. And this essentially how just the derivative of the contact form. Now we have the first structural equation, which is this. It's very similar to the Riemannian case. The difference is that we have torsion, which is non-zero. So you see here, this is a two form. So this is a one form, as I mentioned. And we have the second structural equation, which is the curvature equation. And here we just call it P of alpha beta. That's the curvature. That's a curvature two form. And we have this essentially condition here, this property that also must be satisfied. Now Webster proved that this P of alpha beta is this thing here. And what is this exactly? Well, we use this W notation here for the alpha. Remember how we define the alphas, g of t, x, comma, y. And this is just the coefficients of this thing, okay? And then we define torsion locally in this frame, this coframe. So we write like this. I'm using here Einstein notation, just for compactness. So this is how we define the form, the torsion one form. And we have this identity here. Okay. Okay, now we'll prove a lemma. So essentially what we want to prove is that a property about the torsion, which is this thing here. So g of t x comma y is just g of x comma ty. And g theta is just the Webster metric. Okay, let's prove this. Now, first we differentiate 3. So 3 is just this. We differentiate it and we see, okay, let me go back. If you differentiate this is 0, then you can differentiate this using the product rule. So we get this thing. Then using 4, which is a first structure equation, you can just replace everything here, well, essentially where this appears. And we have this expression. Next, we use this condition, which is the comparability of the Webster metric with the with Tanaka-Webster connection. And this is written locally. You can write this locally as this expression. This is similar to the Riemannian case, but we have h here. Now, h, when we have an orthonormal frame, this will be a constant. So this is 0. But we'll just write it in a more general way. And using 6 and 5, so those expressions, so together, they give this. And we just rearrange this, move this to the other side. We have this. And then, see here, if we rearrange here the wedge products and move to the other side, essentially we have this expression. If we apply this to this frame, we essentially get that A beta M is equals to A M beta. So we have this kind of symmetry kind of property. So now this gives us essentially a restriction when we're trying to compute torsion and the curvature forms and the connection forms. So we can essentially get a unique solution. Otherwise, we wouldn't be able to do that. So we have this restriction here. Okay. Now, we can see that this identity is true. So this torsion tensor is actually written like this: 2 times the contact form wedge, the torsion minus omega, which is omega is just minus d theta when theta is the contact form. So this is just plus d theta essentially, and that's the tensor product with the rib field. And to see this, just all we need to do is just remind ourselves of the definition of the torsion. And just this comes very easily from a definition, so it's not something difficult to see. Yeah, also, so let me go back to the definition. I think it's very back. So yeah, that's the definition. Now, here we define it using the complex, those complex vector fields here, but we can also use the real definition, which would be just 2d theta of xy. So this is essentially times this rib vector field. So using this, we just get this thing. Okay. Next, we prove another lemma, and this is very, very interesting. We have a identity that connects the Tanaka-Webster connection with a Levi-Civita connection of the Webster metric. And this is this identity here. So this connection is the Levi-Civita of the Webster metric, and just nabla. We'll just write nabla here. Previously, I just wrote it nabla TW, but just write like that for simplicity. And we have this times the omega, which is minus d theta, minus a, which is the operator that we defined, the tensor we defined before. Then we tensor product with a Rib field. We add the torsion tensor product with a contact form. And we have 2 times, this is the symmetric product of theta with the J, the CR structure. And it's defined like this. Okay, so let's prove this. Okay, again, we use compatibility of the Webster metric with the Tanaka-Webster connection, and we get this. Now, let's do this trick. Let's take all cyclic permutations of x, y, and z of this identity here, and then just add this y, z, x, and then subtract this z, x, y. So we do this essentially 3 times, and we add by parts, and the last part we just subtract. Okay, then using the definition of the nabla and the torsion, you can get this expression here. And essentially the goal is to create this Koszul formula. So that's our goal here. So that's why we add this cyclic permutation and we subtract this. That will give us the Koszul formula, because here we have, you see, the Lie brackets that comes from the definition. Okay, and then we use the Koszul formula once we identify it, and we get this, which essentially proves our claim. Okay, now this is kind of the main identity that we want to prove here. So we want to see a way to kind of to essentially compare the Tanaka-Webster curvature with the Levi-Civita curvature. So we have this formula here. Let me give some definitions here. So we have this O to be equal to the torsion squared plus 2J, the torsion minus I. And we have this Sxy defined like this. And we define L to be the torsion plus J. So we have this definition, and we get this essentially formula, this identity. So R theta is just the Riemannian curvature of the Webster metric, and this is R just the curvature tensor of the Tanaka-Webster connection. So we see, of course, they're not equal. Now, I should mention something here. Well, let me go back to this identity. Okay, so the previous time I talked about these Riemannian approximants. Now you can see here, if we take, instead of theta, we take just the Riemannian approximants. So we have epsilon theta here, and the t over epsilon. Then we see that as epsilon goes to 0, then this entire thing will go to 0 when projected to the horizontal planes. So don't worry about this term blowing up. We just project to the horizontal planes. So the entire thing goes to 0, and we have that essentially the Tanaka-Webster connection, the Levi-Civita connection converges in this sense to the Tanaka-Webster connection. So those two, essentially this goes to this. And we have essentially that we can use the Riemannian approximants method to compute curvature. This is another way. You can use, you can either use the Tanaka-Webster approach directly, or you can use the Riemannian approach to essentially smooth out and approximate the manifold essentially, and then just take the limit, and you see that it's another way to get the curvature. Now, for the Riemannian approximants method, to me, it's not very clear how to get the torsion. So I don't know, perhaps there is a way, but to me, it's not very obvious how to get this. In Tanaka-Webster's connection, it's very obvious how to get the torsion because it's in the structure equation. So it's easy to get now. Perhaps there's a way to do this in the Riemannian approximants as well. But I don't know. At this moment, I don't know if it's possible. Perhaps it is. Okay, now let's return to this. Again, we see that we have this formula here. Now to prove this, I won't prove this, but the idea, we just use this identity and the definition of the curvature, and after many computations, which are non-trivial, you can get the result. Okay. Now let's talk a little bit about Ricci curvature. Just some definitions. So I won't prove a major result here. Okay, so let's define those functions R of A, B, C, D, written like this from this open set to the complex plane, and we define it using this. So this is the definition. You use this index notation here. And then if alpha is between from 1 to n, then we have that this thing is inside this tangent bundle, this T10 bundle. And in this case, we just get that this function will be 0 when we have S here, this bar S, A, B, C, and when we have 0 here, A, B, C. So this will be 0 in this case. If alpha is equal to bar alpha, then we have those two conditions that are 0, and just use this essentially the nabla of T, the Rib vector field that is equal to 0, then this gives this thing. And now we can go ahead and define the Ricci tensor. So the Ricci tensor, very similarly to the Riemannian case, it's just the trace of this map here for Z, Y, and Z in this TM. And we have this index notation. And we can also define, using the Ricci curvature, the Ricci tensor here, we can define the scalar curvature, which is, we call it rho here, and it's defined like this. So rho is just H A vita bar, and this times this thing here, A alpha vita bar. So this is also the scalar curvature. Now, let's see an example of how to compute curvature in the Heisenberg group. And the Heisenberg group is let me remind you, it's this group C times R with this product, this operation, and we have those left invariant vector fields, which is an orthonormal frame for the Webster metric, is this thing. The contact form is this, and we have a CR structure that satisfies this. Now we have also the non-vanishing Lie brackets. So those are the only brackets we have here, x and y equals to minus 4t. And we can use this knowledge to compute its curvature of the Tanaka-Webster connection. Now let's take this, its coframe. Coframe, if computed, it's just theta 1 is just dx, theta 2 is just dy, and theta is just the contact form. So we have that d theta is 4 dx dy. Now this comes from this. So it's minus 4, so it's actually 4. So we have this. This is the first equation, which is not the first structure equation. It's just the first equation we mentioned when we gave the structure equations for the Tanaka-Webster connection. So we have this, and then let's just try to write the first structure equation. So there are two equations. So essentially, we just want to get the sectional curvature of the planes xy. And we have the following structure equations. So let me just go back to tell you essentially how we do this. Okay, so we just plug in the values here, and we see essentially for the Heisenberg group that this actually vanishes because we have dx here, so derivative of dx is just 0, and we want to compute those forms here. The idea is to just write them in the frame, to write this connection form in the frame we're working, which is theta I, for example. And then just after performing the computations, we just match coefficients. And after some linear algebra, we can just get the connection forms. The coefficients, so essentially will give us the connection forms. So that's what we do here. Omega is just a connection form. And we have the torsion here. These are the torsion terms. Now you see this kind of symmetry here. This looks very much like this, but we have the B term here, and this is the minus A. The reason we have this is because of the, remember here, we proved this thing here. So this essentially helps us compute the torsion as well. So otherwise, we wouldn't get a solution, a unique solution. So we do this, and then, as I said, we just write the connection form in this frame here. Now theta, just write it as theta, so I don't write the entire thing again. And then we just match coefficients, and we hope to compute C1, C2, and C3. And once we do that, we can also essentially try to solve the system. And we use this identity, which comes directly by differentiating this. So together with this, we essentially get that A equals to 0, B equals to 0, and omega equals to 0. Essentially, everything vanishes, even the torsion. And we have a curvature essentially to be 0. Now, the torsion vanishes. So this means that the Heisenberg group is also Sasakian. So perhaps with a rescaling of the orthonormal frame, we can see this more easily. And essentially, that's how we compute the curvature using the structure equations. This is more of a linear algebra problem, and if you know how to compute just the exterior derivative, it's just easier, and just using the Levi-Civita, the covariant derivative, which is more messy, I'd say. Okay, so yeah, that's it. Thank you.